for this very nice invitation, and also congratulate him for this super nice initiative about having this seminar essentially all around the world. So today I'm gonna pick one of my favorite topics, which is Muscat. And well, essentially I'm gonna talk about these two results, very recent results, preprint results. First one is a global well-posedness result for 3D Muscat in the critical subwave space, a result with Omar Lazar. So I'm gonna introduce you that this result in the context of Muscat equation, but also I'm gonna show you that in this problem we can have an unstable situation, and somehow this result give us a global well-posedness result in an unstable situation. And also I'm gonna show you about another global regularity result for gravity unstable Muscat bubbles. This is a joint work with Eduardo Garcia Juarez, Neil Patel, and Bob Strain, where again we have an unstable situation and still we can have global results. Okay, so let me introduce you briefly Muscat. I forgot to say, please let me know, stop me at any time if you have questions. I think I'm not seeing here chat, but yeah, maybe now, no, maybe better like this. So please stop me at any time if you have questions and you want to talk about. Okay, what is Muscat? What is the Muscat problem? Okay, you see here the beach with a very nice wave in the sea, but today I'm not interested on the water wave. I'm interested in the wave. Can you see my pointer? The wave or the contour or the dynamics of this moist region or this interface over here. Okay, you see we have a moist region here in sun. Okay, filter in sun, and here a dry region. Okay, so I want to understand how the dynamics of this interface. Okay, in particular, this kind of problem give a lot of very interesting behavior feature in fluids. So the problem, the kind of problem we study for this Muscat equation are very interesting from the incompressible fluid point of view. Okay, so the questions. After the beautiful photo, the question. So I'm going to consider incompressible fluid, okay, with the incompressible condition. Very fundamental conservation of mass equation. Okay, rho, if you wish, is the density of the fluid, U is the velocity field, okay, incompressibility, conservation of mass. Then finally, I'm gonna close the system with the fundamental Darcy's law. Let's say the most basic equation to model a fluid in porous media. Okay, so we have this water filtering sun. Okay, here in Darcy's law, mu is the viscosity, kappa is the permeability due to the media, U is the velocity field, P is the pressure, G density, as I said, G is gravity, and this is the last canonical vector, ED. Okay, because I'm going to consider 2 and 3D dimensional settings. Okay, so essentially what Darcy's law is telling us is that forces, pressure and gravity, are proportional to momentum. Okay, instead of having second Newton law. Okay, and this is due to the fluid is filtering in the porous media, and then the media is stopping the fluid. Okay, so as you see, what we have over here is a transport equation where velocity and the density are at the same level. Okay, in terms of regularity. What is Muscat? Okay, what is Muskat? This is when we consider two fluids. Okay, so we are going to consider viscosity and density given by these step functions. Okay, given by this step function. These are constant values. So we have two fluids, as I showed you in the pictures, where we have different viscosities and densities. Okay, and let's say they are immiscible. So water, air, or oil and water. Okay, very good. Okay, it's turned out that with this, let's say equation, general equation, I can get an interface equation. I want to model the interface between the two fluids. And I'm gonna, the equation I'm showing you now I'm gonna show you a simpler case, okay? So this is a 3D surface. We have gravity equal to 1. Let's move to a planet with gravity, constant gravity equal to 1. We don't, I mean, just to simplify notation. Permeability equal to 1, constant permeability equal to 1. And we are gonna consider fluid of the same, with the same viscosity, okay? And now I'm gonna parameterize the interface, the common interface between the two fluids with a graph. Sorry, there is a little mistake here. This is a graph, okay? This is a function, okay? So I'm considering a 3D problem between two fluids, so I have a graph, and X is in 2D, okay? Good, so it's not straightforward. So with some cancellation and some tricks, you can get this interface equation, okay, for Muskat. And now we have all these 3 equations with this interface condition resumed in this equation for F, which is non-local, non-linear, and also unbounded, okay, in terms of derivative. Okay, so a lot of very interesting behavior, a very interesting equation. Good, let's see what's going on. So let's linearize, okay? The main reason to show you this equation is because now we can linearize, okay? And well, linearizing here is very easy because you have a square term here. So I'm gonna drop this square term and then I get this linear equation, okay? You can see, or if you go to a harmonic analysis book, you get that the kernel, this guy disappeared. I'm dropping the quadratic term, then I get this kernel, this no local thing here. This guy disappeared because I have here principal value. Okay, the way I understand this equation are with a principal value because they are singular, okay? And then what we get is this risk, the two risk integrals, okay? So this is the first risk integral applied to the first derivative. There is a minus sign that goes here. And then the second risk integral applied to the second derivative. And an important thing here we are gonna see is just that with these two terms, with these two operators, what we get is the lambda operator, the square root of the Laplacian, okay? This has to be seen in the Fourier side, okay, if you wish. Or maybe integration by parts here. And well, an important feature is the difference between the density of the fluid, okay? What we have over here, I'm gonna show you now, solving this equation in using Fourier techniques, is that we have a kind of heat equation, but replacing the Laplacian by the square root of the Laplacian, okay? Good, so let's use Fourier transform, and then what I get is this solution, okay? Fourier transform technique. T is gonna be a parameter, and then C is this is my function on the Fourier side, okay? And what we see is that what we have in if an stable case, when the fluid, the heavier fluid is below, okay, the light fluid is above, okay, and what we have in an unstable situation when the heavier fluid is on top. Actually, what you see here is that at the linear level, this is ill-posed, okay. I can put here a C infinity function initially. Oh, sorry, I have to drop time from here. Sorry for the type. This is the initial data. So there is, I should have right here time. There is no time here. Okay, so I put here the initial data. Okay, and then my initial data can be super smooth, even see infinity, and then this doesn't make sense when time evolves because the exponential is very strong, right? Okay, so remember that what we have is a transport equation, okay, with velocity and density at the same level in terms of regularity. And why this parabolic of this very unstable situation appear? Okay, I don't have time to show you the whole argument to get the equation. Okay, but what we are doing is somehow the fact that the density is constant, we give us that the velocity are analytic, harmonic on each side, in each domain. Okay, so somehow it's like extending what's I did the other way around. You know, I have things on two fluids and then I restrict my equation to the boundary. Going the other way around is like having a function that you want to extend analytically, right? How do we do that with the Poisson kernel? Okay, with a convolution with the Poisson kernel, at least at the linear level. Okay, and why the lambda operator appear? Because the normal derivative or the derivative in the extension parameter gives the lambda operator. Somehow I'm doing something like that, but at a nonlinear level, right? That's the reason why I'm getting a nonlinear equation. Very good. So the Muskat problem modeled this thing. I show you even the question, and it was a pioneering work from the 1934. And also later was compared with a fluid in a Hilly-Shaw cell by Saffman and Taylor. So a Hilly-Shaw cell, you have to, you can see it in this photo, okay? So what you have are two plain glass close enough together, and then you put a fluid in the middle or a couple of fluids in the middle, okay? And then you want to see the evolution, and this two-dimensional feature is mathematically analogous to the feature of Muskat, okay, to the equation, okay? And then here you can do experiments, okay? Okay, so I'm gonna try to give credit to people and then to show you like results. There are a lot. I'm gonna show you in a while with a quick view. I don't have time if I go in many details, so I'm sorry about that, because I want to show you some trick about the result I already told you. But let me start with some classical results. And here I'm sorry, I'm gonna be selfish. The notation I'm gonna use for classical is just when I was undergrad. So I wasn't working on Muscat at all. So this is classical results. Okay, so you see here strong people, very interesting results. And then later, recent results. This is about the problem I just told you. I'm not considering capillarity here, capillarity result here. Okay, later I'm gonna tell you, I'm gonna show you about capillarity. Is the problem I already described is the result. So you can see with a quick, looking at this slide very quick, that a lot of people show up. I'm being like several years without giving talk about Muscat, and then I realized that a lot of people with very interesting results. I have to add to my slides. So very nice. So, and also these are set of paper or published papers, and also there are like mostly from the open preprints. You have over here. Okay, I'm gonna try to give you a quick overview about or summarize this a little bit to have more time to talk about math. So you can get global system for Muscat. Okay, essentially for small initial data, you can have a global system in the stable situation. Let's say when the fluid is above, Or also, you know, the stability and instability has to do with the difference of the viscosities also in the fluid. So this is the Rayleigh-Taylor condition, or the Saffman-Taylor condition, which was proved at the linear level by Saffman and Taylor. Okay, for large data, you can have local systems. Okay, it is imposed, the system, the contour dynamic equation, it is imposed in an unstable regime when this Rayleigh-Taylor condition is not satisfied, when we have denser fluid above, or the most viscous, the less viscous fluid pushing the less viscous fluid. Sorry, the less viscous fluid pushing the more viscous fluid. Even with very, very, very low regular interfaces. Okay, so because of that, there are people trying to understand this kind of situation, this unstable situation, in a more general setting with weak solutions, and then also to try to understand the mixing. The situation I'm telling you is for immiscible fluid, so there is no mixing. There are global systems for small data in a very general setting, in critical situation for critical norms. And critical, there is a scaling. Okay, critical mean with respect to the scaling, and it is related with the slope. Okay, the slope, the L infinity norm of the slope is critical. You have another norm. For example, in 2D, you have Sobolev, homogeneous Sobolev H3 ½ or I don't know, you can pick your favorite space. Okay, there are several of them, but the one for me to understand everything and to have it clear is a slope in L infinity. Okay. Okay, so you have resolving the same in the critical setting. Also, there are conditional blow up. Okay, there are interesting situations when you see the particle which is about to collapse, and then in this setting, it is possible to have some conditional lack of blow up with very light, you know, assumption on regularity. Also, a very interesting feature in fluid mechanics is that for this incompressible setting, here I'm talking all the time with finite energy. Okay, this is a finite energy situation. At infinity, there is nothing going on, and you can check that you have a finite energy situation. So it is possible to have blow up. Okay, so it is possible to have initial graph. Okay, so in this setting between with the density, two different density fluids, you can have a graph. Okay, initially with very large slope, and then you see turning. This turning means that you enter in a stable situation. Okay, you start stable, and you enter in a stable situation, and then later you can have blow up, loss of regularity. Okay, you start very smooth, and then you end up without being that smooth. Okay, being C4, let's say. You start super small, and then you end up being C4. Okay, and also you can have a very interesting non-local behavior, like passing to unstable situation, then going back to a stable situation. Or also you can have, you know, another type of singularity, like turning and then collapsing. I mean, being almost, I mean, two particles very close, so you are not a graph, and then you can collapse. Okay, two particles can collapse. Okay, so when are we going to have local system for low regularity? Okay, this is very interesting to have more and more solution, general solution. So you can have a local system in any subcritical with a lot of subcritical spaces. Okay, subcritical mean like a little bit more regular than critical. Okay, but very as close as you wish to critical. Okay, and also it is possible to have a smoothing in several situations, right? For example, even for high slope, you can have a smoothing with this parabolic with the square root of the Laplacian behavior in the stable case. of course. And you know, there are recent results with very high slope, okay, with very high slope. Some result with monotonic solution, also with in 2D, if the maximum and the minimum of the no, sorry, in 1D interface 1D, if the maximum and the minimum of the slope is smaller than 1, okay, so you need one of both small, then you can have a smoothing and global system. And also there is a pretty recent result due to Córdoba and Lazar, Diego and Omar, in which they prove that you can have a slope very, very high, right? And then norms, subcritical norms, very, very small in Sobolev, and then you can have global systems. This was interesting thinking in the turning scenario, this blowout scenario that I told you, because you can have a global system even for high slope, okay? If you don't have this smaller condition, you can turn and then you can have blow up, okay? And also there is another very recent appropriate super critical result in which you use Sobolev spaces, L2 Sobolev spaces, and then you miss a logarithm of derivative, and then you still can have local systems. So you don't need to have a slope bounded. Here the slope can be infinity. This is a 2D for 1D interface. Okay. Okay, and also there are recent results in which you have you can have critical data with the slope and without the slope. Okay, just measuring in Sobolev, L2 Sobolev. Here you have two results. Okay, so you can have local systems when the slope is very high, or even without the slope. Okay, so a slope can be unbounded, and you have the critical setting here in Sobolev is H3 half. Okay, this result that I already told you are in 2D, 1D interface. Okay, good. So now I can tell you about the result. I wanted to talk you with Omar Lazar. Okay, it's a well-posedness result in 3D. Okay, in a stable situation in 3D. In 3D, the equation for a lot of result is more non-linear, non-local, and harder to deal with. In which we can have initial data in the critical setting in 2D. The Sobolev critical is H2, and then what we have is a Lipschitz solution too. So we have the initial data in H2 and with bounded slope, and the Sobolev norm is small, but you can have the Lipschitz norm very big as you wish. Okay, if this norm is very, very big, then this has to be very, very small. Okay, and the point, an important feature here is just that this result is critical. Okay, so in this setting we can have a global solution for 3D Muskat. Okay, and my interface, the function f is in this setting. Okay, so we preserve the initial space, and also we have a smoothing. Okay, we measure the smoothing in Sobolev. Okay, and we have a solution here for all time. This solution is unique. Well, this is the first result with this feature. Okay, with large Lipschitz class in 3D, and also being critical. It gives smoothing, and also the technique or the ideas that we use can be extended to 2D. Okay, can be extended to the two-dimensional setting. So having a different proof of the result that I already told you. Good. I'm not doing well with time, but somehow I would like to show you some ideas. Okay, some ideas. This is a technical result in which you have to look for, because it's critical, a lot of cancellation and commutators But let me show you some ideas. Okay, so we rewrite the contour equation like this using this incremental. Okay, this is like derivative. Okay, what we measure over here in this incremental fraction is the derivative. Okay, and please believe this is 3D Muskat. Okay, and why this? Well, we are gonna integrating this thing, we can get like half derivative, which is good for us because we have this fractional dissipation, and also we are looking for critical results. So we have to share derivative very nicely. So we are gonna use this best of setting that allows, you know, to share derivative very well. So here I'm using this incremental with the delta with this notation, and we have here fractional derivative for NES. So this is the best of a space. PQ, I have to move to two indices, and S is the derivative. Okay, with this LP of this thing to the power Q, and then again this integral. Okay, we don't have to scare. We have to be scary about this. Best of is highly common, no? Nowadays in PDs. And for example, if I took P and Q equal to 2, I recover usual Sobolev, okay, for S between 0 and 1, okay? And okay, you see that this incremental thing, or this fraction on this delta YF appear in Muskat, okay? Okay, so now the point is just that if we compute the evolution of the H2 norm, which is the critical thing we want to control, by brutal force, we don't find anything bounded, okay? So what we're gonna use is an Omar Lazar idea. Let's try to look for, he did first in 2D, now we are gonna try to push 3D. So let's try to look for oscillation. Oscillation is going to bring us cancellation, and then hopefully this cancellation is going to bring us the inequality that we need in this evolution. Okay, so we are going to have rewrite again the Muskat non-local equation with an oscillatory term and with an oscillatory integral. Okay, if you integrate this and then you simplify these two trigonometric equation, you recover what we already had. Okay, and why? Well, we have to suffer a lot and to look for a lot of cancellation, and Omar now a lot how to do these tricks, and is very good at doing that. But summarizing a lot, one idea is just to look for higher derivative with this symmetric incremental thing. You know, if we symmetrize at the Sobolev level the norms, we can get higher norms, and this is going to help us to share derivative in an appropriate way. We are symmetrizing, right, and then we can reach, if we think in the Taylor expansion, we can reach higher norms, right? Well, then after a lot of efforts, looking for a lot of cancellation in this trigonometric function, combining sine, cosine, sine of sine on cosine, symmetries, and commutators, and a lot of Sobolev's of Besov estimates and Besov injection in different spaces, then we end up with this inequality. Okay, I'm more or less lucky because Omar gave a seminar in this Zoom PD seminar, so if you need more detail, you can even look at his talk. Okay, and then I have somehow dissipation. We get somehow dissipation in this inequality, but depending on the slope. Okay, have L infinity here. And then what we want, or what we really would like to have, is this thing small. Okay, this is the nonlinearity. This thing is this H2 norm is small, so that we can absorb this term that tell us how this norm can grow, this H2 norm can grow with the dissipation, okay? But in order to do that, I need to control the slope, okay? Everything is critical here, and I cannot control the slope with the H2 or the H2 H5 half norms, okay? So what I'm gonna do a trick to control the slope, okay? I'm gonna write Muskat with a tricky integration by parts like this, okay? And now I can understand Muskat like with a transport term with a no-local velocity given by this part, and then kind of a no-local dissipation, okay? So what I'm gonna do is to take one derivative because I need to control slope. We need to control slope, right? So taking one derivative, I'm gonna take one derivative to the transport term, okay? One derivative to the kind of dissipation term, no local dissipation. I'm rewriting everything so that you can understand, believe my calculation, and then a mixed term, okay, in which where I hit this no local part downstairs. When I hit the derivative, I get something like this. Okay, and what I'm gonna do now is just to check the evolution of the maximum. Let's say M is gonna be the maximum of the slope. Okay, it's gonna be finite, and I'm gonna reach this maximum at a point I'm gonna call xt. Okay. If F is regular enough, with some technique, Rademacher technique, being a little bit careful, I can check that the evolution of the maximum M prime of this maximum is given by this. I have to be careful, right? Because I have this, I cannot have this even for super regular functions. I cannot have this point-wise. I'm gonna have this for almost every time t. But it's okay because later we are going to integrate, okay? So in this equation, I'm gonna evaluate at xt. So very good, this gives me M prime of t for almost every time here. This guy disappeared because I have the gradient of the derivative j of f of xt. So at the maximum, this is 0. Okay, the gradient has to be 0 because it's a maximum. Here I have the appropriate sign. This is kind of a no local dissipation. And this have the appropriate sign. Here I have the maximum, and here I have another value. So this have a sign which is in our favor, is helping us. And then what I have to control is this guy, this term over here. This term, if you think, is like mostly cubic, but you see that they have this fraction here and then another fraction here downstairs, so I can cancel this guy. This guy is not cubic, is gonna be at the end quadratic with derivative here and derivative here, because this guy is bounded if I consider this whole fraction I'm showing you. This can be bounded by 1, let's say, total force bounded by 1. Actually, it's bounded by 1/3, even a better bound. I don't care. The point is just that this term is not cubic, it's quadratic. Okay, so I have a term with a sign, I have a term that disappears, and then a term that I can bound. I'm gonna show you the bound of this term. So one thing disappears, another guy with the right sign, and then the bound of a quadratic term. Believe me, please, it's not a difficult computation that you have something like that. It is evaluated at the maximum. I'm gonna do L infinity. It's evaluated at xt, where the function, the derivative takes on the maximum value, but I'm gonna take L infinity. Okay, I don't care anymore about the point. I'm gonna take L infinity. Good. I'm gonna put all the singular part here, and then I'm just gonna do Helder. Okay, I'm gonna get something like that. And I can realize, doing a little bit of effort, but not too much, that this is less than or equal, or probably equal, to the gradient of f in a Sobolev norm, in a Besov norm, with the exponent q L infinity. That the spawning, sorry, P coming from the L infinity here. Okay. Then I use embedding. We use embedding because we are in dimension 2. And then we have something like that. We use embedding. And then at the end, I'm very happy because what I have is the L2 norm, and is given by the gain of regularity I'm having. Okay. The parabolic regularity I'm getting from the equation. Okay. And at the power I need, power 2 that I need, that I hope to control. This is just the best of embedding in case you don't remember that. So I can do the same for the minimum, and then later I'm going to integrate. Remember that this is for almost every time, so I integrate, and I can have the infinite norm initially, and then the nice thing is just that I integrate this in time, and I have the hope to have this power. Because of this power, I hope to have this integral control. Okay? Very good. So I plug this control of the L infinity norm into the equation I told you before, and then I'm calling this dissipative thing like fancy D T, okay? And remember that this start being 0, okay? Of course, what I'm gonna do now is a kind of bootstrapping argument, so I need somehow regular solutions. So I'm gonna regularize the system with a Laplacian, and I'm gonna keep all the estimate that I have. I'm gonna be able to have smoothing the initial data. I'm gonna be able to have global existence, okay, for this system because of the regularization of the Laplacian, and then later I'm gonna take epsilon to 0. I'm gonna have, for regular solution, I'm gonna have the same thing, okay, for the critical solution that I want to get, okay. So the conditions that I'm plugging here is for me to preserve. This is what we want. Omar and I want to preserve this inequality, right, and to absorb this thing into the dissipation. Okay, so having these conditions, which are on the slope and are also on the initial H2 norm. So we're gonna have, if you wish, after a short time, this decreasing, the H2 norm decreasing, and then the dissipation less than 1. Okay, and then integrating in time, at the end we are going to conclude that we are going to have this for all time. Okay, and then this is going to be bounded by this for all time, and then the dissipation is going to be less than 1. The dissipation thing, H5 half derivative, is going to be bounded by 1 for all time. Okay, and with this, I conclude this first part. I still have time, so please let me know if you have questions. Hopefully this is not just me talking and then you have time to think about, but let me know if you have questions about all this stuff, okay? Because now I'm gonna move to a slightly different setting, keeping the problem. Okay, good. So now I'm gonna move to surface station effect in the Muskat problem. Okay, so I'm gonna deal with capillarity. So in a lot of experiment, you see the classical is the Saffman and Taylor experiment. It is possible to see what is called fingering. Is when you see, for example, in this picture, these fingers going on, and this is because of the Rayleigh-Taylor condition. This unstable condition is not satisfied, but still you have immiscible fluids which are unstable, and then this evolved with this very I don't know, fractal pattern of showing this fingering. Okay, and this is experimentally, or this is understood with the adding to the system surface tension or capillarity, because we have small bubbles or small drops, small fluids, and then we see into the small scale we see this pattern. And this is you know, a force. I'm just introducing a force because due to we have two fluids of different nature. Okay, and this gives the Laplace-Young condition, which is super classical condition in this case. Okay. Very good. So I have to give you, I don't have too much time, but I have to give you some some recent result, or what I said, not classical, recent result on capillarity, capillarity Muskat. Okay, so the point is that mathematically, when you have a pure and stable situation, by this I mean that the Rayleigh-Taylor has the bad sign. Okay, so Rayleigh-Taylor, so essentially think that you have the denser fluid above. Okay, and then you put capillarity, you still are going to have local system of solutions, but then it is possible to have an unstable situation. But unstable, I mean, for short time, the time you can control the equation, you are seeing exponential growth for the slope, let's say. So this is possible. This has been proved. Also, there are some bubble settings, but without gravity due to those guys. And okay, the feature on the main interesting thing I'm gonna describe to you next is when we have gravity. Okay, gravity is gonna move the bubbles I'm going to consider. You can have also without gravity drops having, you know, contact points with solid, air, and water. Also, there is people try to understand how surface tension, when surface tension coefficient goes to 0 in a stable situation, how to approach the capillarity Muskat to the Muskat I told you at the very beginning of this talk. Recently, we were able to in a stable situation, to handle with enough surface tension, but critically to have global regularity in a critical setting, dealing with fixed boundaries, having smoothing and you know, this was studied a lot in different regimes, doing homogenization or providing different models. We did for the whole Muskat, okay, without any model. Also, people try to understand this setting, this fingering, given with solutions. And also there is recent result due to Hui and Nguyen, in which he got local system in any subcritical case, okay, being as close as critical as you wish. Critical, I mean, in terms of the scaling. Here with capillarity there is no scaling, but somehow you can have a scaling similar to the one without capillarity, okay. And also there is convergence in any subcritical case, very sharp result due to Flynn and Hui and Nguyen. When surface tension goes to 0, recovering a stable situation from capillarity solution. Okay. Okay, good. So what I want to talk about in the remaining term, how much time do I have? Like 10 minutes?
You have 10 minutes. Okay. You have 10 minutes.
Okay. Okay. It's okay, 10 minutes?
Yeah.
Okay.
Yeah. It's okay. 10.
Okay. So I'm gonna consider bubbles moving by gravity. Okay. This is a very unstable situation because all the time you have a bubble. We're gonna have a bubble. So in some part we are gonna have a denser fluid above another. Okay. I'm gonna have capillarity because I need capillarity for a bubble to model a bubble. So in particular, I want to model how bubbles move, and I would like to show you a video to see a very interesting phenomena about bubbles in Muscat. This is a beach, of course, and you see water coming. When water came strongly with a strong wave, filter inside the sand. I don't understand how. I would like to understand, but I don't understand how mathematically bubble creates, air bubble creates. And then later you see that because of gravity, bubbles came up, and you see on the sand bubbles coming out and then blowing up. I don't understand quite well how bubbles blows up, how bubbles form with a corner or maybe, but you see that you see bubbles coming up because of gravity and then later blow up. So I'm gonna show you a result, not how they form because this is difficult for me or how they blow up, but I'm gonna show you how they move, okay? So let me stop this video. Good. So let me go a bit quick on the free boundary equation. Let's put this better. It's gonna be seen better. Okay. So now I'm gonna move to 2D. So 1D interface, one bubble. We see the flat bubble. And then this is the equation. Essentially, it's similar, but they have more feature. I have difference of viscosity, I have surface tension, I have gravity, okay? And I have capillarity. I have not only surface tension coefficient, also I have curvature or derivative of curvature, okay? So this omega is just the amplitude of the vorticity. We're going to have a vorticity concentrated on the interface, and it's given by this non-local relation using double layer potential, if you prefer, of the Dirichlet-Newman map, as you wish, and then moving Muskat, which move in the normal direction. Okay. Good. So this is a highly unstable situation because what measures this unstable situation is Rayleigh-Taylor, and the Rayleigh-Taylor condition has been 0, so we cannot have a sign. We cannot have a denser fluid above. Also, we cannot have a more viscous fluid moving a less viscous fluid. Okay, so it's very unstable. But we can show that even in this unstable situation that is imposed without surface tension, in this unstable situation, we can have bubbles which are circle that move with gravity. So this is a steady solution, completely unstable. If without surface tension we modify a little bit the solutions, this is completely imposed, okay? But the circle, the Sachs circle, is a solution here, even without surface tension, okay? And this solution, you see the solution moving up with gravity, depending of if you have a denser bubble, then the bubble go down, and if you have a less dense bubble, the bubble go up. Okay. Okay. So for me, this was very surprising with surface tension, with a surface tension, and then we try to take advantage of this steady state, and what we are able to prove, and we were able to prove, is global existence near, more or less near, with a wide range of parameter near this steady state, unstable steady state. Very good. So this is the result. This is what I already told you. Okay. So if we have an initial interface which is close to a circle, a bubble close to a circle, this close means that I mean, we have, depending on some constant on the system, of course, but the constant of the system are dimensionless. Depending on this is the Agut number with the viscosity. We have here gravity divided by surface tension. This R is essentially length. So R squared is essentially area. Okay. So we can find that the solution exists for all time. And we have the smoothing. We have decay. We have low regularity and things, this kind of things. Okay. And so what we see is a bubble that can say, we see that its move can move like this, but the shape is preserved. Okay, move up, but also can move a little bit like this in the meantime, going up. Okay, I have 4 minutes, I think, for for give you some ideas on some ingredient of the proof. So, okay, this really Taylor condition that doesn't have a sign is a mess. I mean, at least for me, it's hard to understand because sometimes it's helping you, sometimes it's not helping you. So at the end, a nice way of trying to understand this is using Fourier techniques, okay? So doing Fourier to the equation. But if we do Fourier to this kind of perturbation, right, we have something close to the circle. This is something close to the circle moving up or down, okay? Then we see a chaos in the evolution of the Fourier coefficient. For example, in the 1 and -1, we don't see dissipation. The dissipation we are trying to get is from surface station, okay? But we cannot get it essentially because you have other representation of the circle and this is natural. Now that we see, that we understand this phenomenon is something natural. So we are gonna use another way of understanding our bubble, which is not a Lagrangian way, right? It's gonna be, we are gonna look at the tangential vector, okay, that describes the bubble. And then we are gonna look for a particular way we can do this, reparametrization the interface, having, you see, a constant. This only depends, the modulus of the tangent vector only depend on time here, okay? So this is the length, this LT is the length of the bubble, okay? And then we are gonna look for the equation of theta. Theta gives me the angle. If theta is 0, you have here a circle, okay? The tangential vector of a circle, okay? And then curvature is gonna have this nice structure, and then we are gonna be able to, these have been used, okay, by other people doing numerical simulation, also getting local system and things like that, okay? Well, but remember, please take a look at, if we take a look of this approach of this equation. For example, constant value, if we put different constant value for theta or first of 0 Fourier coefficient, what we are doing is translating, okay? So we cannot see dissipation in that. Okay, so what we are gonna use to avoid this thing is to have this compatibility condition. Essentially, it's telling us that this has been 0, and then I'm gonna put the condition that I impose. I'm using here complex variables, and then you can see the trick I'm gonna show you easily. Then this thing cancel out. I can put this here, multiply by or divide by this cancel out because this is equal to 0, okay? And also I can get rid of the 0 Fourier coefficient because this is another constant that I can take out of the exponential and then cancel out. Good. Even more, I can get the 1 and -1 with this condition, with this compatibility condition. It is possible to get the 1 and -1 Fourier coefficient of theta in terms of the other. And this is good. Because at the linear level, when we do a lot of math, this is very hard work, we get the dissipation, and you can see that there is no dissipation for 1 and -1 Fourier mode. But it is okay because 1 and -1 is going to be in terms of the other, and the other decay, okay, at the linear level. There is something curious here that the second coefficient is different because of a special integral we get. Okay, and at the end, this is the system that we have. I just want to show you the system with, we can control the length using the incompressibility. We have this compatibility condition, and then we have the linear system that we can control with the nonlinear term, and then we control the 0 mode. This is essentially a tangential term that we can control. Here, the 0 coefficient does not appear, so we can control it with the other. And then we have this bubble that move up and down, having solution. But it turned out that by brutal force, and I'm gonna finish now. By brutal force, in this system, we cannot get solution for any range of parameter of this parameter, a dimensionless parameter. It doesn't matter how small is the initial data, okay? So we have to do an extra trick, okay? So we have to do a kind of diagonalization in this nonlinear setting and to put an equivalent norm, and then with this equivalent norm, we are able to get this bubble. So we're gonna have, according to these parameters, we're gonna have a initial data small enough so that we are gonna have global solutions. So I don't know, I don't have time. This is the general theorem with all the setting and all the, we can discuss later if you are interested. I would like to thank you very much for your attention and for following the talk.